Hello, and thank you for watching. I am Fong Yuan Yang from the National University of Singapore. Today I will present our CVPR 2026 work, HumanBA, Human-Aware Bundle Adjustment via Global Human Camera Decoupling. The goal is to recover both camera motion and global human motion from ordinary monocular videos, especially when the human occupies a large part of the scene. In Human Mesh Recovery, or HMR, the aim is to estimate the 3D mesh of the entire human body from an input video, like the example on the left. Usually, the recovered 3D mesh is local, meaning that it sits only in the camera coordinate space. What we would like to recover is the mesh in world coordinates. This is what we call global HMR. The problem is that the observed video is produced by both human motion and camera motion. The human moves in the world, and the camera also moves in the world. Together, they produce the same image space observations. Because these two motions are entangled, many different global setups, such as the red and purple examples shown here, can lead to the same video. So how can we disentangle the two motion components? One strategy is a purely data-driven local-to-global approach, which learns a mapping from local motion cues to a global trajectory. These methods try to infer what the global motion should be based on local observations of motion and velocity. The predicted trajectory can then be composed with local human motion to recover global motion. But such methods can fail under ambiguous observations. For example, in this skateboarding sequence from Wham, the feet are almost stationary on the skateboard, so the local motion suggests that the person only sways back and forth. However, in the world, the person should actually be moving forward. A more ideal solution is to explicitly model camera motion and fully decompose the two components. This is closely related to monocular SLAM, a well-studied problem in 3D vision and robotics. Modern SLAM methods, such as DROID SLAM and DPVO, can estimate camera motion quite well in many cases. However, classic SLAM assumes a mostly static scene. Recent global HMR methods therefore mask the moving human before running SLAM. This preserves the static scene assumption, but it also removes many useful observations, especially when the person occupies a large part of the image. This motivates our question: can the dynamic human become a useful constraint instead of an outlier? The key idea of HumanBA is simple. The human is an outlier only before motion decoupling. If we estimate and remove the human-induced component from the observed joint trajectories, the remaining signal is camera-induced. These pseudo-static human landmarks can then be safely used as bundle adjustment targets, together with ordinary scene landmarks. This is especially useful when background constraints are weak or heavily masked. Here is the overall pipeline. We first obtain initial camera estimates from SLAM and local human estimates from an HMR model. We lift the human into world coordinates, construct pseudo-static human targets, and assign motion-aware weights. These targets are added to the standard bundle adjustment objective. After the camera poses are updated, we recompute global human motion and rebuild the targets for the next iteration. This creates a mutually reinforcing loop. The target construction is the core of HumanBA. For a bundle adjustment pair I and J, we want the human from time I expressed in camera J. We start from the observed human in frame J and subtract the human-induced world displacement, transformed into camera J coordinates. After projection, these pseudo-static points become two-dimensional human-aware bundle adjustment targets. Intuitively, we remove the person's own motion and keep the camera-induced component. Because bundle adjustment is sensitive to bad references, HumanBA does not treat all human joints equally. We use joint acceleration over the bundle adjustment pair as an instability proxy. Joints that move abruptly, or pairs with larger accumulated uncertainty, receive lower confidence. The final optimization combines standard scene residuals with weighted human residuals, and then updates the camera and global human motion iteratively. We first look at camera trajectories. Compared with the masked baseline, HumanBA reduces drift and helps mitigate abrupt trajectory jumps. The robustness analysis further supports the motivation. When the human occupies more of the frame, masking removes more observations. In this regime, HumanBA provides larger gains because it recovers useful geometric constraints from the human foreground instead of discarding them. Better camera motion also improves global human motion. In the visualization, HumanBA produces a more stable world space human trajectory than TRAM. Quantitatively, on EMDB2, HumanBA achieves the best global human metrics, including WMPJP, and root translation error. Since the local HMR model is unchanged, these gains mainly come from better global alignment and camera estimation. The adaptive weights also behave as intended. Kinematically, proximal joints such as the pelvis and hips receive higher weights than distal limbs like hands, which are more flexible and noisy. Temporally, shorter bundle adjustment pairs receive higher weights than longer pairs, where uncertainty accumulates. This confirms that HumanBA uses human-derived constraints selectively, rather than blindly trusting all joints. To summarize, HumanBA shows that dynamic humans can improve SLAM when properly modeled. First, motion decoupling turns observed human joints into pseudo-static bundle adjustment targets. Second, motion-aware weights select reliable joints and temporal pairs. Third, the improved camera trajectory feeds back to produce better world coordinate human motion. Thank you for watching, and please visit our project page for code and more results.